Okay, let's now consider the null space of a non-singular matrix. So remind yourself of what a null space is. I just skipped back to this page. What page is it? Page 61. And here's the definition of null space right here. The null space of a matrix is called N of A. It's the set of vectors that are solutions of the homogeneous system. So the null space, I could write this way. N of A is equal to the set of vectors X such that AX is equal to the trivial vector. Okay, so that's the null space of the matrix A. Okay, we see some examples of this. We can look at the null space of a singular matrix. Go back to this example and see that this matrix reduced to a non-identity matrix, and it turned out that the solution was parameterized in terms of x3. x3 was a free variable. So this is the null space. It's simply the set of solutions to the linear equation. Okay, and all right, so here null space of a non-singular matrix. We do the same thing with this second example. When we reduced this A, you got the identity, which meant that the solution set for the homogeneous system of equations was the trivial solution. So we only got the trivial solution. Okay, so it should be clear that if you have a non-singular matrix whose only solution is the trivial vector, then the null space is the trivial vector. Okay, so that's what we say here. Non-singular matrices have trivial null spaces. So we're really saying the same thing we said above using this new language of null space. Okay, suppose A is a square matrix, then A is non-singular if and only if the null space of A is the set containing the only the zero vector. That's another way of saying that it has a trivial solution. Okay, and you can read this proof, but really it's what we've discussed up here. All right, so here, now we're going to pull several things together. Okay, so we talked about how the non-singular matrices, when you take the homogeneous linear system associated with a non-singular matrix, you get only the trivial solution. It turns out that no matter what the right-hand side is, no matter what B is when you have AX equals B, if A is non-singular, then B is unique. If A is non-singular, then, if A is non-singular, then X is unique. There's only one solution for this system, no matter what B is. B can be anything, any vector at all. Okay, very interesting theorem. That no matter what vector constants I put here, if A is a non-singular matrix, I can find a solution. And this should agree with your experience of equations with variables, that usually if you have, say, 3 equations and 3 variables, no matter, many times, no matter what you put in for the constants, you can find a solution. Okay, and so this expresses the case exactly when you can always find a solution, no matter what the constants are. Right. Now, notice that in this proof, let's go through what he writes here. This proof has an if and only if. And whenever you have an if and only if, you have to prove 2 different ways. Okay. Now, first he's going to prove this way. Now, this way corresponds to the if. This is a little confusing because usually when you read a statement, you say if blah, then blah. But here we're saying blah, if blah. So when you say, so you're saying if the system LS has a unique solution. That's what we're assuming, that's our supposition, and we want to show that this means that A is non-singular. Okay, so we have to suppose, to prove this implication, we have to suppose that the system LS of AB, that this system here, has a unique solution for every choice of B. Okay, all right, now, here he says we'll make a very specific choice of B equal to 0. Okay? If this is true for any b, then in particular it's true for 0. Okay? And that implies that LS of A0 has a unique solution. But that's just the definition of what non-singular means. Okay? So this way, sometimes when you prove if and only if proofs, one way is much easier than the other. That's the case here. In fact, you could say that this is just a special case of what you're trying to prove here. So in other words, if LS of A0 contains a unique vector, then LS of AB will also contain a unique vector. Now we have to show the other way. The other way is the only if. Now, the way you should think about only if means that if this first implication, then the second implication. Sorry about all the junk here. Let me remove it. All right, so I'll keep this here to remind us this is B can be anything, and X is unique. X is unique. Okay? Okay, so now we're trying to prove the other way. Let me scroll down a little bit. We're trying to prove this implication here. So that means we're assuming the first statement and deriving the second statement. So this is where we want to go. We start with A as non-singular. We want to show that AX equals B has a unique solution no matter what B is. Okay, so here we go. Suppose A is non-singular. Okay. If it's non-singular, then it row reduces to the identity matrix. Okay. When you take the augmented matrix and row reduce it, then the matrix of coefficients will row reduce to the identity matrix. The vector of constants, we don't know what it row reduces to, but it row reduces to something. Doesn't really matter what it is. Now, when you have this row reduced form, you can read off the solution. It says x1 will be equal to c1, x2 will be equal to c2. Let me draw a little picture. Okay, I guess I can draw the picture down here. If I have I and c here, then you can see what the matrix looks like. You're going to have 1s on the diagonal, 0s below, 0 above, and then I have c1 is the first one here, and I can call the last one cn. And we know enough to read the solution off of this matrix. x1 equals c1, x2 equals c2, etc., etc. Okay, so we do get a unique solution. Okay, so we started with A as non-singular, and we ended up with a unique solution. That completes the proof. We're all done. Okay, so this shows why we're very interested in non-singular matrices. Often we do want to find a unique solution to a system of equations. Okay, now, this theorem applies to non-singular matrices. It also has implications for singular matrices. Okay. Now, a singular matrix means that for at least one value of B, this system, AX equals B, does not have a unique solution. Okay. Now, there's more to be said about singular matrices, which will be proven in a later theorem. Now, it turns out that there are many, many ways to describe non-singular matrices. We've already seen several of them. We've seen that A is non-singular if and only if it row reduces to the identity matrix. And we've also seen that A is non-singular if and only if its null space contains only the 0 vector. And we've seen that A is non-singular if and only if the linear system LSAB has a unique solution. So these are all equivalent by the theorems that we've shown. Okay, and here he wonders why a matrix is non-singular when it has a single solution. Well, singular means special, so non-singular means not special. So in some ways, this is the usual situation when you have a square matrix. But we'll see more about that later.